discussion. Melvin Leok is going to tell us about variational discretizations of gauge field theories using group-equivariant interpolation.
All right, thank you. So I'd like to thank the organizers for the invitation to speak here. It's a great pleasure to be back at the Newton Institute. So this is joint work with Evan Golick, James Hall, and Jars Frankenschafer, who were all at the University of California at San Diego. It's like with me at some point in time, and very generously funded by the National Science Foundation, and more recently by the Air Force. So let me try to contextualize what we're interested in doing. Of course, you probably know that gravitational waves are ripples in the fabric of space-time, and they were predicted by Einstein. It's in 1916. And of course, it's what's really, I think, excited many people in the community is that gravitational waves were directly observed. It's in 2015. It's by the LIGO project. And as we've already heard, it's during this conference, numerical relativity is necessary to compute black hole mergers that generate these gravitational waves. It's primarily a view towards constructing templates. It's for gravitational wave detection. And more importantly, it's the inverse problem of how do you relate observed sort of gravitational wave signatures. It's with astrophysical events. Okay, so let me try to frame the problem. It's from a variational perspective, because that's going to be related to the kind of discretization which we're interested in developing. So you can think of the Einstein equations as arising from the Einstein-Hilbert action, and it's given here, and it's defined in terms of Lorentzian metrics. And if you look at the corresponding Euler-Lagrange equations to that action, you get the Einstein field equations, which are here. And some things which immediately sort of leap out is that this is a second-order theory, so it depends on essentially second derivatives. It's of the metric, and it's a gauge field theory in the sense that if you apply space-time diffeomorphisms, it's the problem, then the action stays invariant. Okay. All right. So what a gauge symmetry is basically is a continuous local transformation on the field variables, and that which leaves the system physically indistinguishable. And one consequence of having a gauge symmetry in the problem is that the Euler-Lagrange equations are in some sense underdetermined, in the sense that the evolution equations themselves are insufficient to propagate all the fields. And there is a decomposition, if you will, of the fields into sort of two classes, one of which are kinematic fields, which have no physical significance. If you're coming from geometric mechanics, then you might think of these as the group variables, if you will. And then it's the dynamical fields and the conjugate momenta are the ones which have physical significance. So in the language of geometric mechanics, those would be shape variables. And there's another sense in which the Euler-Lagrange equations are overdetermined. And in particular, it's when you specify initial data on a Cauchy surface, then it has to satisfy a constraint, typically elliptic. And Mike, for example, talked about yesterday about the Einstein constraint equations. And trying to solve for these initial value problems. So there's a sense in which the symmetry leads to sort of a class of degenerate systems. And I'm going to try to convince you that the natural framework for doing this from a variational perspective is what is called multi-Dirac mechanics and geometry. Okay, so let's look at an example of a gauge theory. So this is for electromagnetism. You have the E and B fields, the electromagnetic fields, and you can write down Maxwell's equations in terms, of course, in terms of the scalar potential and the vector potential. And it has the following form, and you can then verify that the following gauge transformation leaves the equations invariant, where the gauge transformation is defined in terms of this scale valued function f in space and time. And some of the pieces which show up, of course, are these Cauchy initial data constraints. It's on the initial data. Okay, and this just means the B field as the initial time and the E field at initial time satisfies these equations. So the indeterminacy, it's due to the gauge freedom in the field theory, can be fixed, if you will, as through the choice of a gauge condition. So there are different choices of gauge which show up, for example, in Maxwell. You have the Lorentz gauge, which is given here, and that sort of gives you something which essentially looks like a wave equation. It's in the scalar and vector potentials. And then you have the Coulomb gauge, which is given here. Okay, So the real problem, if you will, it's like is that if you ever tried to solve it's like these equations analytically, then you probably know that given different initial and boundary conditions, some problems are easier to solve in certain gauges as opposed to others. And there's no real systematic way of deciding which gauge to use for a given problem. It's like until you sort of, unless you know sort of what the problem looks like, which is sort of a chicken and egg problem. And this is a little bit disturbing, if you will, because if you're trying to do things numerically, then there's a sense in which you don't fully understand what to expect. It's like in the solutions. And so it sort of raises the question whether, you know, one, it's like whether sort of this idea that you fix the gauge and then it's like develop discretization, whether that's always a strategy which makes sense, or whether, you know, ideally it's like there's a sense in which you could choose the gauge adaptively as you do the simulation, right? So that's sort of an ongoing question which we're sort of grappling with. I'm not going to say we have good answers to that, but I at least want to throw it out there and say, I mean, it's like, is it? I mean, it's like, you know, one should start looking at numerical methods, if you will, without presupposing a choice of gauge. Right? All right. Anyway, so what are the consequences of symmetry? So in mechanics, of course, you are probably familiar with this idea of Noether's theorem. So if there is a continuous symmetry of the action, then there's an associated Noether quantity which is conserved in time. And the simplest example of this is if you have an action which is time invariant, then the associated Noether quantity is the Hamiltonian. And a time invariant Lagrangian Hamiltonian system has the Hamiltonian as an invariant of motion. All right. So in the sort of in the gauge theory setting, it's like if you have a gauge symmetry, then there is a Noether current which comes from this gauge symmetry, which satisfies a continuity equation. Okay, and if you integrate this Noether current over a space-like surface with the appropriate boundary conditions, then you have a conserved quantity known as the Noether charge. Okay, so for electromagnetism, these are the Noether currents, and in the case of the Einstein-Hilbert action, for general relativity with the space-time diffeomorphism symmetry, then the stress energy tensor is the Noether charge for this. Okay, so what are the consequences, if you will, of gauge invariance in general relativity? As in addition to the usual Noether's first theorem, which you might be familiar with, there is that's what's known as Noether's second theorem. And so Noether's second theorem says that if you have a problem with gauge symmetry, then the all Lagrange equations are not functionally independent, right? So there's some functional dependence between this, and it manifests itself in GR by the fact that if you look at the Einstein equations, only 6 of the 10 components of the Einstein equations are independent. And so typically, it's like we've heard this talked about. This is typically, it's like addressed by imposing some sort of gauge condition, for example, the maximal slicing gauge or the Donder harmonic gauge. And we heard about the use of harmonic gauge and generalized harmonic gauge. It's like in, say, gravitational wave simulations, for example. And if you formulate this as an initial value problem, then the initial Cauchy data is constrained. And in particular, in general relativity, it's like there are the Gauss-Cardazzi equations, which have to be satisfied. So, so another way of thinking about this from a variational perspective is that you have a degenerate variational principle. So there's a sort of equivalence class of solutions that's like which satisfy the variational principle. So it's not unique. So, so what does that then suggest? It's like when it comes to numerics. So when you look at relativity, of course, it's like the general covariance. It's like if the system plays a really fundamental role, so from our perspective, which is sort of a finite element-based approach, this sort of naturally suggests that you might want to avoid the use of sort of globally sort of tensor product space-time discretizations, which presuppose a global slicing of space-time. So instead, it's like we would like to build our approach, it's like on some sort of simplicial space-time mesh. And then it's like, as opposed to the usual finite element approach where you think of getting the discrete equations from some sort of weak formulation, if you will, of the equations, we're going to try to look at this from a variational perspective. And in particular, we're going to consider it's like what we call multi-Dirac mechanics, which is based on a generalization of Hamilton's principle to field theories. And I will sort of allude to why this is well adapted to degenerate field theories. And so I should mention I come from geometric mechanics, geometric integration. So in particular, it's like we would like to then construct sort of symmetry gauge and invariant discretizations using this variational discretization framework. And in particular, it uses a set of approximation spaces which are gauge equivariant. And I'll say a little bit more about this. And the reason why these gauge equivariant space-time finite elements are useful is because they lead to a gauge invariant variational discretization, and then the gauge invariant variational discretization satisfies a discrete Noether theorem, which leads to a multimomentum conservation law. So that's sort of the general approach we'll take. Okay, so let me try to illustrate this idea of the Hamilton-Pontryagin or Dirac approach to mechanics in the case of mechanics. So you, instead of the usual Lagrangian formulation, which is prescribed in terms of position and velocity, or the Hamiltonian formulation prescribed in terms of position and momentum, we're going to look at some combination of the two. And so we're going to introduce what's called the Pontryagin bundle, which is this kind of fiber product of the tangent bundle and the cotangent bundle. So it has local coordinates, position, velocity, and momentum. Okay? And then we're going to introduce a variational principle on this. So this is sort of like the usual Hamilton's principle. There's a Lagrangian, which depends on position and velocity. But I'm no longer going to assume that velocity is the time derivative of the position. I'm going to relax that condition. So you should think of Q and V, formally speaking, as being independent. But I'm going to impose, it's like the condition that V is related to Q dot via Lagrange multiplier. And I'm going to suggestively choose P as the Lagrange multiplier, and you'll see why in a second. And so this, if you will, is just, it's like a Lagrange multiplier version, it's like of the usual Hamilton's principle. Okay? All right, so you take variations in Q, V, and P. It's like you use the standard integration by parts kind of construction. It's like based on the assumption that the variations of position vanish at the endpoints, and you end up with sort of these implicit or Lagrange equations. Okay, and you can easily convince yourself that if you eliminate the velocity variables and the V variables and the momentum variables P, then you get the usual or Lagrange equation, right? This says that the time derivative of dl dq dot is equal to dl dq, which is the usual Lagrange equations. So you might say it's like, well, what do you gain? It's like by trying to formulate Lagrangian mechanics this way. And what you gain is that if you have a Lagrangian which is degenerate, for example, it's only linear in velocities as opposed to quadratic in the velocities, then this condition here, that P is equal to dl dv, right? Usually it's like what happens is that this relationship between the velocities and the momenta, right? That relationship's invertible, okay? So if, however, the Lagrangian is not hyperregular, then this thing is not globally invertible. And so the condition, this then becomes a constraint, if you will, in the evolution. Okay, so this is what is called the primary constraint condition. In some sense, what happens then is that if you have a degenerate problem, actually imposing the equations in this implicit form, it's like give you the additional constraints, which basically say that the momentum is in the image of the Legendre transform. And so it allows you to write down the equations without then having to separately augment, it's like the usual second order form of the Lagrange equations with the primary constraint condition. Okay, so that's sort of, if you will, motivation for why you might consider this, particularly in the context of degenerate Lagrangian systems. So let me sort of then briefly say how you do this for field theories. Okay, so if you have some space-time, some n+1 dimensional space-time, which I denote as X, which is the base space, then you have over space-time, it's like the fields over that. So this is a configuration bundle. And you want a configuration of this. So basically what you want is, morally speaking, you want to map, it's like from every space-time point to the field value associated with that. Okay. So in the language, it's like of fiber bundles, this is a section, it's like of this configuration bundle. And then it's like you want something which gives you information about how the derivatives, it's like in the fields, sort of how they behave. And so you write this down in terms of what is known as the first jet bundle of this. Okay, so it's the bundle which consists of the space-time points, the field values, as well as the first partial derivatives of the fields with respect to the space-time directions. Okay. So if you have these pieces, now it's time to introduce some physics to the problem. It's like, can you introduce the physics using a Lagrangian density? So Lagrangian density takes something in the first jet bundle and gives you an n+1 differential form on the base space. Okay, and so you can integrate that over some domain. It's like on the base space to give you the action, and then the usual Hamilton's principle states that the variation of this action is stationary, subject to fixed boundary conditions on the boundary of the space-time domain. Okay, so this is what is called the multisymplectic framework, and this is in contrast to the sort of the instantaneous canonical formulation of Hamiltonian PDEs, right? So the other sort of very common way of dealing with Hamiltonian PDEs is to just imagine time as being the only independent variable. At any time point, it's like you have a function that's like of space, which tells you it's like what the few values are in all of space, okay? And so, sorry. And the let me sort of briefly say why it is that you might want to consider it's like the multisymplectic formulation instead of the usual sort of infinite dimensional canonical formulation. And so Ari yesterday spoke about semi-discretization in the context of Hamiltonian PDEs, right? So the usual way it's like one approaches Hamiltonian PDEs is you semi-discretize in space, and then you do sort of a method lines approach. And that's certainly fine. But that naturally leads to a global tensor product space-time mesh, right? So why is that a problem? If you do something like elasticity, then you of course have the CFL condition. And if you have slivers, which are sort of badly shaped elements in your mesh, then this sort of imposes a very restrictive time step restriction. And this has to be globally applied, even if only one sliver exists in the entire discretization. Okay? So what the multisymplectic framework does is it puts in a very, very rigorous framework, it gives you a sort of a nice setting. It's like for describing discretizations which are not globally space-time tensor product discretizations. You could have local discretizations on space and time. Okay, so it talks about how you do this. All right. So anyway, so this is sort of the usual Lagrangian multisymplectic formulation of field theories. Now I'll briefly say something about how you do this Hamilton-Pontryagin version, which is sort of the Dirac or multi-Dirac formulation. So you do the usual thing. You have a Lagrangian density. It's like, so I've written this in local coordinates. You have a Lagrangian density, which depends on the space-time points, the field values, and the derivatives of the fields. And I've, again, formally assumed that the derivatives of the fields are decoupled from the field values themselves, but I've reimposed the relationship here with a Lagrange multiplier. And then this is what is called a multimomentum. And you get the implicit all Lagrange equations as before. And then what's interesting is that because of the sort of affine structure, it's like of the dual first jet bundle, the Legendre transform, right, associated with this includes both the usual momentum maps, it's like as well as the energy terms. So it encodes both the energy and the momentum terms as well. Okay, so that's sort of a brief introduction to sort of the continuous theory, if you will. And so now let me say something about how we're going to propose to discretize this. So given the fundamental role of gauge symmetries and the associated conservation laws in gauge field theories, it's really natural to consider discretizations that respect it's like these properties. As we heard from Ari yesterday, it's like geometric integrators are a class of numerical methods that preserve geometric properties. Examples of these include symplecticity, momentum maps, or maybe it's like the configuration spaces themselves. It's like live in some sort of curved space, for example, a Lie group of homogeneous space, and you want to respect that in some way, shape, or form. And what one typically sees is that this typically results in numerical simulations with better long-time numerical stability and better qualitative agreement to the exact flow. Okay, so now let me sort of dig in a little bit deeper and give you one systematic way of constructing. It's like a class of geometric integrators, which are called variational integrators. And they're based, again, on discretizing Hamilton's principle. So as you might recall, Hamilton's principle basically states that if you have an initial point and a final point, then the trajectory which connects those 2 points is that which extremizes the action integral, which is the integral of kinetic minus potential energy. Okay, so one way to discretize this is to imagine sampling it's like points along this trajectory by a set of discrete points here. Then you introduce what is called the you introduce what's called the discrete Lagrangian, which you should think of morally as the approximation of the action integral over a small time interval. Okay, so imagine instead of the action integral over the entire trajectory, you imagine action integral just from q0 to q1. Okay, and ideally, it's like you would like to approximate what is called the exact discrete Lagrangian, which is the following object. It's the action integral evaluated along some distinguished curve, and that curve satisfies the all Lagrange equations and is compatible with the boundary conditions which I specify q0, q1. So if I specify q0, q1, and I specify the Lagrangian, then there's some curve which satisfies this all Lagrange boundary, or is the solution of the all Lagrange boundary value problem. And if I evaluate the action integral on that, I get what is called the exact discrete Lagrangian. And this is really nothing more than Jacobi's solution to the Hamilton-Jacobi equation. So the reason what's called the exact discrete Lagrangian is that then that object is the generating function of the exact time h flow of the problem. Okay, so anyway, so if you have some approximation of this exact discrete Lagrangian and you sum it all up across this sort of pairs of points, then you get an approximation of the action integral, and you can introduce a discrete version of Hamilton's principle, which then says that the variation of the action sum is stationary, subject to fixed endpoint conditions. And when you write down the corresponding sort of stationarity conditions, you get what is called the discrete all Lagrange equation, which is given here. And you should think of this d2 as the derivative with respect to the second slot. So in this first term here, it says the partial with respect to the second slot is qk. So this is the partial with respect to qk of LD, qk minus 1 qk. And then this is the same thing, partial with respect to qk of LD, qk, qk plus 1. Okay? So this you can think of as being a two-step method, which defines a map from qk minus 1 qk to qk, qk plus 1. And you can check that this map is symplectic in a precise sense by introducing sort of momentum variables. Okay? And then it's very, very clear that this is equivalent to the usual characterization of a symplectic map in terms of type 1 generating functions. And if it's not already obvious, you really should think of the discrete Lagrangian as a type 1 generating function of a symplectic map. Okay, and so it's like this has been applied, it's like to a bunch of problems. So this is Taeyang Lee, who was a former student of mine, who's now at George Washington. And together we've applied this to a bunch of problems arising in mechanics, astrodynamics, fluids, and so on. And Todd Murphy at Northwestern, it's like has applied sort of similar ideas to biomechanical systems, human prosthetics. So he works with the Rehabilitation Institute of Chicago. It's like to model human prosthetics, for example. And you can extend this to the PDE setting via this multisymplectic framework which we discussed. And you can apply this to plasticity, elasticity, strings, and so on. This is due to Eitan Greenspan at Columbia. Okay, so let me sort of focus now on why it is that you want to construct this a numerical integrator in this way. What does it buy you, both in terms of conservation properties as well as error analysis. Okay, so the first thing is, of course, a discrete version of Noether's theorem. Okay, so if your discrete Lagrangian, if you could construct your discrete Lagrangian in such a way that it respects the symmetry, okay, in the following sense, if you have initial data q0, q1, and you transform it in via some group action, and that discrete Lagrangian is invariant under this diagonal group action, then there's an associated discrete momentum map which is preserved by the flow. Okay? So that's the discrete analog of Noether's theorem. And then the second thing is that you have this object which is the exact discrete Lagrangian, which formally generates the exact time flow. And you can ask to what extent your numerically computable discrete Lagrangian approximates this exact discrete Lagrangian. So implicitly, these things both depend on the time step. So if those things are related by sort of an error term which depends on the time step to some power, then you can show that the corresponding symplectic maps approximate each other to the same order of accuracy as well. So it reduces the problem of error analysis of a symplectic integrator to something about the error properties of a scalar value function. And oftentimes this is a much easier thing to do. Okay? And in fact, you don't even need to do this because we've developed certain Noether theorems which basically tell you that there is a way to construct these methods with those kind of approximation properties from appropriate choices of approximation spaces. Okay, so I'm going to sort of do a brief aside and say that the other motivation for looking at symplectic or variational integrators is that they are sort of closely related to adjoint sensitivity analysis. So if you're going to try to solve inverse problems and you want to do sort of adjoint sort of methods, then it turns out that even if your original system of equations don't have a Hamiltonian structure, the adjoint system, it's like where you take the original equations and the adjoint equations together have a Hamiltonian structure. And that symplecticity is essential to maintaining this relationship between the primal and the adjoint variables. And this is a result due to Chus and Cerna, and it was reported in this paper in Science Review back in 2016. And the other thing which is quite interesting is that it turns out that these methods are connected to optimization and machine learning as well. So that's what's known as Nestrov's accelerated optimization scheme. And there's a paper which I forgot to cite. It's like due to Michael Jordan and his collaborators at Berkeley, which showed that the Nestrov method can be viewed as a discretization of the flow of what is called the Bregman-Lagrangian or Hamiltonian. And it turns out that it also turns out there are connections between discrete mechanics and information geometry, which are in turn connected to machine learning. So this is something which I wrote together with Jin Zhang. It's like at Michigan. Okay, so this is so if you don't care about mechanics, you don't care about. It turns out that even if you're interested in sort of much broader questions like optimization, learning, it's like and adjoint sensitivity analysis, it's like sort of structure preserving methods play an interesting role there as well. Okay, anyhow. All right, so let's get back to variational integrators. So the question is, how do you construct a computable approximation of this exact discrete Lagrangian and then say something about the error properties? Okay, so I'm going to reformulate. It's like the exact discrete Lagrangian. Previously, I'd said that it was involved evaluating the action integral along the solution of the Lagrange boundary value problem. Now I'm going to write this variationally and say that it's the sort of the extremal, if you will, of the action over the class of twice differentiable curves satisfying the boundary conditions. And it's clear that this is equivalent to the usual formulation because the stationarity condition for this is really just the Lagrange equation. Okay, so what I do now is I replace this twice differentiable family of twice differentiable curves, which is an infinite dimensional function space, with some suitable finite dimensional function space. I replace the integral with a quadrature rule. And now you can imagine that I can solve that problem to give you a computable discrete Lagrangian. And so what's perhaps important to note is that variational integrators don't always preserve momentum. You have to build that into the system. Okay, so and in this framework where I replaced the integral over quadrature rule and I replaced the function space with some finite dimensional function space, the way you construct variational integrators, it's like which preserve momentum, is by choosing what are called group-equivariant function spaces. So imagine that you have a way of taking a bunch of control points and then giving a curve associated with that. All right, so this is sort of so if you parameterize, if you will, it's like your finite dimensional function space by a set of control points, and you take those control points and you transform them, say, by a rotation, all right, and then have a new curve which goes through or is related to that, then the old and new curve should be related by the same rotation. Okay, and if it is, it's like then you say that this construction, this finite dimensional function space, parameterized finite dimensional function space, is equivariant with respect to this kind of group action. Okay, and if you use those kind of group equivariant finite sort of function spaces, then you get a G-invariant discrete Lagrangian, and via discrete Noether's theorem, you get a momentum-preserving integrator. Okay, so that's something which isn't so difficult to do in the ODE setting. It's much more subtle in the PDE setting, and I'll sort of talk about how you do that. Okay, so let me say something about error analysis. Okay, so you've constructed the numerical method by a suitable choice of a finite-dimensional function space, right? So what and a big part, if you will, it's like of numerical analysis is this sort of, synergistic connection, if you will, of approximation theory. And so that's what we're going to try to do, right? So you've chosen a finite dimensional function space. So what would be nice is if you could say something about the numerical error which you get and frame that in terms of what is called the best approximation error. So if I have the exact solution, I want to ask to what extent this is well approximated by something in this finite dimensional function space, and I can look at this error in some perfect norm. And if with respect to the same norm, right, it's like the error between the exact solution and my numerical solution is bounded by some multiple of this best approximation error, then what that basically is saying is that if I did, say, a posteriori error analysis, it's like on the solution, it's like of a PDE or an ODE, and then from that I know some regularity properties of the solution, and then I use approximation theory to tell me that with respect to this sort of function space, if you will. It's like I can approximate this to a certain rate of accuracy by some sort of sequence of approximation spaces. Then I can use this knowledge, it's like to construct a variational integrator with certain nice approximation properties as well, right? So it reduces the problem, if you will, of systematically constructing variational integrators to one of approximation theory. Okay, so the area analysis of this, it's like involves essentially proving gamma convergence of the discrete Lagrangian, because the discrete Lagrangians I've constructed, it's like involve sort of a variational principle. But not just that, I have to relate the rate of gamma convergence, it's like to this best approximation error. And it turns out that you can do this, and you do this by basically refining, it's like a result due to Michael Ortiz and Stefan Mueller, where they showed that variational integrators are gamma converge, okay? And if you're sort of look at it more carefully, it's like you can show that then that these variational integrators in this construction don't just gamma converge, but that they're order optimal and that the spectral versions of these are geometrically convergent. Okay, so anyway, so what that basically tells you then is if you were to use, for example, polynomials of fixed degree, of increasing fixed degree, it's like you'll see that they converge at faster and faster rates, okay? This is sort of what happens when you do what is sometimes called p-refinement, where you fix the time step and you let the polynomial order increase. And this shows you that when you do p-refinement, then the error it's like converges geometrically. And if you notice, of course, I've drawn two lines here, and I have two different sets of markers. One's a circle and one's a cross. Okay, the circles tell you it's like the rate of error convergence at the multiples of the time step. It's the usual kind of error analysis one does. It's like for variational integrators. But notice that when we constructed this computable discrete Lagrangian, I chose a distinguished element of the finite dimensional function space in order to construct this value, right? So you can ask whether that distinguished element of the finite dimensional function space is a good approximation within the time interval in some L infinity sense. It's like to the original solution. And it turns out that it is, and you can, when you do the error analysis, you show that this L infinity error, it's like of this sort of piecewise solution, if you will, within the interior of the time step, converges at half the rate, it's like of the approximations at the endpoints, okay? So, but what's interesting is that you don't really notice that slower rate of convergence until you're fairly well resolved, okay? But it does indeed converge at a slower rate. So what are the implications of this? So you apply this to the n-body problem, right? So this is some approximation of the inner solar system. And what I've done here is that I've taken time steps of 100 days, and you probably know that so Mercury is in this simulation. Mercury has an orbital period of about 81 days. I've taken a time step which is larger than the orbital period of the fastest thing that shows up in this. And yet I don't get absolute garbage. And the reason I don't get absolute garbage is because I've chosen, it's like an approximation space with 25 Chebyshev polynomials, which is rich enough to capture basically the entire trajectory, okay? And basically by the error analysis, which we discussed before, that's somehow good enough, it's like for you to capture the entire dynamics and then take steps which are larger, again, than the fastest orbital period. Okay, and the same thing is true, it's like with the outer solar system approximation here, where I've taken a time step of about 5 years, and again, this is faster than the fastest orbital period, which is resolved in the problem. Okay. You can apply this to the setting, it's like of Lie groups as well. So here, the black dots correspond to samples of the trajectory, it's like at multiples of the time step, and then the thin black lines correspond to this interior approximating solution, which was used to construct the discrete Lagrangian, and again, it does a very nice job of interpolating inside these points. Okay, all right. So, so this is the free rigid body problem. Okay, so in the body fixed angular momentum representation, and you probably know that the free rigid body has two invariants, one of which is the energy, and the other which is the sort of spatial angular momentum. But because I'm in the body angular momentum frame, what happens is that the magnitude of the body angular momentum is fixed. Okay, so what happens is that the dynamics of the rigid body, it's like evolves on two surfaces, one of which is the energy ellipsoid, and the other which is the momentum sphere. And if you take the momentum sphere, you intersect it with energy ellipsoids of greater and greater value, then you get it's like these kind of lines which you see here, which tell you that the long and short axis are stable, and then the middle axis is a saddle point, and so you get this middle axis instability, which you might be familiar with. So in any case, if you apply sort of explicit Euler to this, you sort of see that rapidly these invariants are violated. If you applied ODE 45, it's like, and you really sort of crank up the it's like the tolerances so that it's as precise as it could possibly be. You have a much slower, it's like drift off the constraint manifold, but nevertheless there is a drift off the constraint manifold. And if you were to take one of these variational integrators and then adapt it so that it evolves in the Lie group, you'll see that it does a really excellent job of respecting those invariants. Okay. All right. So it's like, so yesterday it's like there was some discussion about adaptivity and how it's like you can't naively it's like construct symplectic methods it's like in a time adaptive way. So let me say how you can actually do this in a more careful way. So if you have a Hamiltonian and you have some prescribed it's like transformation, it's like between your sort of computational time and your physical time, it's like given by this sort of monitor function G, then you can introduce a new Hamiltonian system which is given by what's called a Poincare transform in the following way. This was something which was introduced in sort of in this paper by Ernst Tyrer. It's like, and I think it's like Sebastian Reich it's like did something which was contemporary to this as well. In any case, so what you can get is like you get these following sort of Hamilton's equations, all right? And if you look at the sort of the solution corresponding to the modified energy, it's like being 0, it's like then it's like then you get the solution which you want. It's like corresponding to this sort of time adapted or sort of time transformed version of the solution. And the problem, if you will, is that you typically end up getting a degenerate Hamiltonian. So this is the second derivative of the Hamiltonian in respect to the or the modified Hamiltonian or sort of augmented Hamiltonian in respect to the sort of augmented momentum. And basically this thing is not full rank. And so you have to be a little bit careful because the error analysis assumes everything is hyperregular. But you can show that if you use what are called Hamiltonian variational integrators, that as long as the original untransformed problem was hyperregular, then this new thing it's like can be inverted in some way if you do it carefully. Okay, so in particular, it's like this sort of regularity condition holds true if you have a non-degenerate Hamiltonian and if you have monitor functions which don't depend on the momentum. If they just depend on the position, then you're fine. Okay, so I sort of alluded to this idea of Hamiltonian variational integrators. Let me say a bit about how you can construct this. So the idea is that, of course, you have a Hamiltonian which is mapped from the cotangent bundle to the rails, and it's degenerate if the Lagrangian transform is non-invertible. So if you have a degenerate Hamiltonian, then of course you can't do the usual trick of doing a Lagrangian transform to the Lagrangian representation and then using this prescription we had to construct a discrete Lagrangian. And if you really wanted to, then doing a Lagrangian transform back to give you a type 2 generating function, for example. Okay? So what I would like to do is to directly go from a Hamiltonian to a type 2 generating function, which commutes with which allows this diagram to commute if you have hyperregularity, but nevertheless still makes sense when the Hamiltonian is degenerate. Okay? All right, and let me just sort of say it's like a bit about why it is this is, it's like a non-trivial problem. So if you have a Hamiltonian, this toy Hamiltonian, which is just position times momentum, then you can check that the Lagrangian transform is clearly non-invertible because it maps QP to just Q and Q, so it loses all information about the momentum. And then the associated Lagrangian is identically 0, so even if you're willing to try to compute this, it doesn't give you any useful information about the dynamics. If that doesn't convince you, if you write down the Hamilton's equations, you have this with the following exact solutions, and these exact solutions are incompatible with the prescription of the initial and the final position for a fixed time interval, right? Because it's like if you look at this, I can specify initial time, the initial value Q0 But once I have that and I know what the final time is, then I have no freedom, it's like to specify Q1. So in general, I can't construct this exact type 1 generating function. So what the take-home message is that, well, you would like to construct a variational integrator purely from the Hamiltonian side, and the object which you end up getting shouldn't be a type 1 generating function. It should be a type 2 or type 3 generating function. Okay, so how do you do that? So you start with the usual exact discrete Lagrangian, all right? And the first thing you do is that instead of writing it in terms of Lagrangian, write it in terms of the Hamiltonian using the standard Legendre transform. And then, so now formally speaking, it's like you have a type 1 generating function in terms of the Hamiltonian. So you want to convert that to a type 2 generating function, but then doing another type of Legendre transform. It's like where you convert type 1 to type 2, okay? And then this is what is called the exact discrete Hamiltonian, okay? And you want to go about discretizing this to construct a Hamiltonian variational integrator. And you can prove that, if you choose the same approximation spaces and you choose the same quadrature rule, that this is equivalent to the Lagrangian formulation. It makes that diagram I showed before commute as long as you have hyperregularity, okay? But even if you don't have hyperregularity, this still makes sense for a degenerate Hamiltonian. All right, so I've talked a lot about ODEs. It's like, let me try to sort of circle back and talk about PDEs. All right, so what are the PD analogs of these sort of implicit characterizations of symplectic maps in terms of generating functions? All right, so the reason why these, of course, are useful is because it gives you a very, very simple way of proving that the flows are symplectic. You just take the second exterior derivative of the discrete Lagrangian and apply it's like one of these conditions, then you can check that this is obviously equal to 0 because d squared is 0. Then this is really just the difference of the symplectic maps at the two endpoints. And so that tells you that the map is symplectic. All right, so if you have this exact discrete Lagrangian, what I would like to do is I would like to introduce what I call the boundary Lagrangian. So morally speaking, what's happening here is that if you, in the ODE case, it's like you have some solution curve and you specify the data at the endpoints of the time interval, at the initial and final time. So you want to do something similar, it's like in the PDE setting. So what I have as the input data to this boundary Lagrangian, if you will, is the field values on the boundary of a space-time domain. Okay, and given that data, I want to write down the value of that really is just the action associated with some section of this configuration bundle which satisfies the boundary conditions which I've prescribed here and satisfies the Lagrange equations in the interior. Okay, and of course you can do this variationally as well in the same way. So that tells you what the candidate boundary Lagrangian is, and you can ask, well, what is the analog of these kind of equations? So you can do a calculation, and you can check that when you take the variation of this respect to changing the boundary data on a point on the boundary, then you get this following object. So it can't possibly just be the multimomentum because the multimomentum doesn't have the same dimension as the fields, right? Because you're taking derivatives of the fields with respect to space-time directions. So they're going to be n plus 1 times, it's like, so multimomentum is n plus 1 times, it's like the components, it's like of the field variables, okay? So what could happen is that you can look at the normal component, if you will, of the multimomentum, because you're only doing this on the boundary of a space-time domain. And this is more or less what it is, right? I mean, it's like more precisely, it is a codimension 1 differential form. But if you have some sort of metric, it's like, you can then identify this with the normal component of the multimomentum. Okay, and so this condition on every point of the boundary of a space-time domain is then the multisymplectic analog, it's like, of this usual generating function condition. Okay, so that then sort of allows you to think about, it's like variational integrators for Hamiltonian PDEs. It's like in this sort of more abstract framework. Okay. And in the same way, it's like in the ODE theory, it's like there's a type 2 version of this, it's like which is given here, and then there are the associated equations here. Okay, so again, the hope is that it's like you could combine it's like these sort of type 2 generating functionals, it's like to construct discretizations of Hamiltonian PDEs, and then possibly see to what extent you can incorporate these Poincare transform versions, it's like to give you sort of space-time adaptive methods, right? So this is something we haven't done yet, it's like, but would be interesting to do. All right, so you have a discrete Noether's theorem, you have a systematic way of constructing group invariant Reed's discrete Lagrangians, again, in the same way. And, you know, it's like, and again, the art, it's like in constructing these group invariant discretizations is to construct group-equivariant discretizations of the function spaces, okay? So circling back, it's like to relativity, it's like you have a Lagrangian density which depends, it's like on second derivatives, it's like of Lorentzian metric value data, okay? So the question is, how do you construct maps from space-time meshes to Lorentzian metrics in such a way that it's equivariant with respect to some rigidification of the space-time diffeomorphism group, okay? All right. So the spatial Lorentzian metrics, of course, are these 4x4 matrices which are symmetric, sort of have non-zero determinant, and have this kind of signature, okay? And you want it to be an interpolant in the sense that if you specify on the vertices of some space-time, it's like simplex, it's like the metric data, you would like the interpolant applied to those points to recover the data you've prescribed. You want the interpolant, it's like at any point, it's like in this sort of simplex, it's like to be in the space of Lorentzian metrics, and you'd like that if you conjugate the data by something in the sort of indefinite orthogonal group, that the interpolant gets conjugated as well. And so this is, so morally you should think of this as a rigid sort of action, it's like of the diffeomorphism group, it's like on this simplex, and this is, you know, it's like, so this is what is necessary, if you will, it's like in order to get this equivariance. This is, well, let me rephrase that. This is a statement of the equivariance, and this is what's necessary to get a method which then respects the symmetry, okay? All right, so you might ask, it's like, why is this hard, okay? So let's look at these two Lorentzian metrics. And let's look at the sort of the naive thing where I just look at the sort of the average, it's like of these things component by component. Then you can check that you get this other matrix here which is not in the space of Lorentzian metrics, okay? So that naively component-wise interpolating, it's like these things, it's like don't necessarily stay, it's like in the space of Lorentzian metrics. Okay, so it's not signature preserving. So one way to do this is to construct what are called geodesic finite elements. So this works for anything which takes values in a Riemannian manifold, okay? So you might ask, wait, it's like I'm looking at the space of Lorentzian metrics, but it turns out that the space of Lorentzian metrics can be endowed with a Riemannian metric structure, okay? And it's because it's a symmetric space. Anyhow, so if you have some scalar valued shape functions, you construct this sort of, you know, it's like weighted sum, if you will, of which penalizes the mismatch between the data which is prescribed and then the candidate value of the Lorentzian metric, and you want to minimize this, it's like over the class of Lorentzian metrics, and the arg minimizer of this is what you output, it's like as a finite element value. Okay, so the problem with this, of course, is that this is extremely expensive because every time you evaluate this finite element, you have to solve this minimization problem on the space of Lorentzian metrics. So it turns out that that's, you could do this, but it's extremely expensive. Okay, so what we've done instead is to sort of think about, well, you know, what we would have done, it's like if we had a Lie group, right? So if we had a Lie group, it's like then the usual construction is to use things like exponential maps and sort of canonical coordinates of the first kind, and basically to identify everything on this nonlinear space, it's like with the Lie algebra, which is a linear space, okay? Of course, the reality is that, you know, the space of Lorentzian metrics is not a Lie group, but it is a symmetric space, and so there's a similar construction. So it's not a symmetric, it's not a Lie group, but there's a similar construction, if you will. And that similar construction is like relies, it's like on this idea of generalized polar decomposition, it's like which was used by Hans Reinhold and Anna, it's Antonella, it's like in sort of this paper here. So the basic idea, if you will, is that if you have a symmetric space, there's an analog of the usual polar decomposition. So if, right, so it's like you can write down, it's like this matrix, it's like as something, it's like in the space of J symmetric matrices, and something, it's like in this sort of indefinite orthogonal group, all right? And, yep, And the associated tangent spaces, like to do these two spaces, it's like one of which is a Lie algebra. This other thing here, the tangent space to this, is what's called a Lie triple system. Okay. All right. So I mean, the upshot, if you will, is that it's like given something in the space of Lorentzian metrics, you can identify it with a bunch of local diffeomorphisms. There's something in sort of this Lie triple system, and the point is that a Lie triple system is a linear space. And so if you pull all the data back, you do interpolation here, and then you sort of push it back to the space of Lorentzian metrics, you get a nice interpolant with certain nice properties. Okay, so the upshot of this is the following kind of interpolation formula. And what we need is that there's a scalar-valued interpolant here, which satisfies some Kronecker delta property. And basically, if this scalar-valued interpolant has certain approximation properties, then it induces, it's like the same approximation properties, it's like on this Lorentzian metric-valued interpolant. Okay? And in particular, it's like the interpolant is signature preserving, and so if you start with Lorentzian metric value data, you end up with Lorentzian metric value data, and then it has this frame invariance property that if you conjugate, it's like the data by this indefinite orthogonal matrix, it's like then the interpolant gets conjugated as well. Okay, so we haven't put all the pieces together, but we've tried, it's like these interpolants, it's like and applied it to the Schwarzschild metric. And if you start off with linear shape functions, it's like as your underlying, it's like scalar-valued interpolant, it's like then you can check the L2 and H1 errors with respect to the analytical solution, and it converges, it's like in the rate you expect it to. And it also, you also always get sort of, metrics which are actually Lorentzian metrics, right, and not just Riemannian metrics. And if you did quadratic shape functions, then it has the higher rate of convergence in L2 and H1, which you expect. Okay. And it turns out that these things are related to other kind of interpolants. If you sort of modify the construction in a slight way, then you can show that it's related to this geodesic finite element construction. If you replace J, it's like by just the identity matrix, it's like then what you get is the usual construction for symmetric positive definite matrices, which have shown up in the literature before. Okay, so it's a fairly, it's like, so the method is sort of fairly broad. It's like it applies to a whole bunch of symmetric spaces. Yeah, sorry. It's not global. It's local. Yeah, it's local. Yeah, so there's no getting. So the data has to be sort of close together. Yeah. So, yeah, it's not global. I guess I see. So I should say that. Right. So if you, so we just assume that the data is close together, right? But yeah, as it's written, it's like you can ask whether the log exists, right? So you can, I mean, there's a way to transform it so that as long as the data is close together, it's like you're just sort of looking at a near identity-like thing. Yeah. So I should have mentioned it, but yes. Okay. Anyway. So let me try to summarize by saying that gauge field theories exhibit gauge symmetries that impose Cauchy value initial value constraints, and they're also underdetermined, and they result in degenerate field theories. And I've sort of tried to at least motivate why it is that we think that this generalization of Lagrangian Hamiltonian mechanics, it's like called multi-direct mechanics and multi-direct structures, is the relevant framework for studying degenerate problems. And that there's a systematic framework for constructing and analyzing Reed's variational integrators, how to do time-adaptive methods, and how to extend this to Hamiltonian PDEs. I talked briefly about how you construct multi-momentum preserving variational integrators, and in particular, it's like why they rely, it's like on sort of group-equivariant finite element spaces, and in the context of potentially applying this to general relativity, we discussed how you construct sort of space-time finite elements taking values in symmetric spaces, in particular Lorentzian metrics, using a generalized polar decomposition. So let me stop here. Thank you.
Okay, we have
Oh, it's Schwarzschild. I'm sorry. Yes. So what happens is that you have the Schwarzschild solution. We sampled it at sort of nodes of some mesh, and then we interpolated it using our method, and then you checked it's like what the error was. It's like of the approximation, right? So sure. Sure. Mm-hmm. Sure. Right. Sure. Yeah. So what we're going to do is that we're going to take these interpolation methods. We're going to combine these with these Dirac variational integrators to discretize the Einstein-Hilbert action. And then what that would do is that it would give you a discretization that respects this rigidification. It's like component, sort of cell by cell wise. It's like of the spacetime diffeomorphism symmetry. And then that will preserve a multimomentum map, which is related, it's like, to the symmetries, it's like, which generate that. So it's just to demonstrate that the interpolant you get has the kind of approximation properties you expect it to. I mean, this has all been proven. I mean, it's just. Sure, we didn't evaluate it there. I mean, it's, yeah, we didn't cover that part. Yeah, so it's just to demonstrate that numerically that the theoretical result which says that if you have certain approximation properties for the underlying scalar valued interpolant, that the Lorentzian metric valued interpolant has the same approximation properties. Okay, and that's something which we've proved. It's like, but I mean, it's sort of just nice to demonstrate that numerically as well, right? So it doesn't, yeah, I mean, it's like, it's got nothing to do with Schwarzschild solution. I mean, it's like all it does is to check that the interpolants still stay in the space of Lorentzian metrics, okay, and two, that it has the right approximation rates, right? And then if you couple that with the sort of these variational error analysis results and this sort of meta theorem which we stated, it's like about best approximation errors, right? When you put all these things together, then what that's telling you, right, is that you can then construct arbitrarily high order approximations based on, you know, it's like choosing scalar valued interpolants with the appropriate regularity properties or appropriate approximation properties, and then you can do this in a variational way, and it will respect it's like the momentum preservation properties. Yeah, does that answer your question? Yeah.
Any other question? Yeah. Yes, I have a question concerning the best approximation.
Right.
Can you maybe say a few words to what kind of problems it applies?
To what kind of problems it applies to? Yeah, so the problem, if you will, is that the usual variational error analysis says that if you can approximate this exact discrete Lagrangian by a computable discrete Lagrangian, right, that your numerical method has the same approximation properties. It doesn't tell you how to construct one of those things. So what the best approximation result tells you, or let me rephrase that, what the result which says that the error of the discrete Lagrangian, how the error of discrete Lagrangian is related to this approximation tells you is that, you know, if you know something about the, so for example, if you know that, you know, it's like the solution is going to decay, is going to stay in some regularity class, then you might want to choose, it's like approximation spaces which approximate that regularity class well, right? So for example, if you have something which is real analytic, right, then you use sort of some sort of spectral approximation. It's like it will have the spectral rate of convergence. And as a practical application, you know, when we applied it, it's like to the n-body problem, right, it does show it's like that spectral rate of convergence when you do p refinement. So the Lagrangian has to be, yeah, so, right. So the Lagrangian has to be, so we proved this specifically for when the Lagrangian is quadratic kinetic energy minus potential, right? So it's sort of this canonical form of it. Because there's, yeah, so when you do the error analysis, it's like there's a certain estimate. It's like you have to be able to show. It's like, and you can show that for that class of Lagrangians You might be able to show it for other classes of Lagrangians, but you showed it for that class.